Hi, everyone. Welcome back to MAT1841. So what did we do last time? Well, last time we started talking about wavelets. What we wanted to get an orthonormal basis on the vector space of functions. And you have already seen that in the form of a Fourier series or the Fourier transform. But that has some disadvantages because it doesn't have locality of its support. And so like sine waves have continuous support across the entire real axis. So instead, we've been building up to constructing something called wavelets, which will allow us to give an orthonormal basis for the space of functions that has finite support. And what we left off with last time was defining something called a dilation, which just scales all distances by some factor. So it might shrink it. Well, generally, we're talking about shrinking it. And a dilation equation, which is a function that's defined in terms of these shifted scaled versions of itself. So there is this really easy example of just a scaling where the function, which is 1 between 0 and 1, 0 everywhere else, well, you can define that as two scaled copies of itself, one that's 1/2 and starting at 0 to 0.5, and the other that's the same size, but starting from 0.5 to 1. And of course, there are more complicated examples of that, one of which was this triangular shaped function that we see here, which you can redefine as three shifted and scaled copies of itself. So now that we have that, so there are these non-trivial examples. And we're going to spend some time today talking both about the properties of these dilation equations in general. So first, we're going to prove something about this general form of dilation equations that are shifted by a factor of 2. And then we're going to spend more time and actually construct an orthonormal basis set out of this particular really simple example of a dilation equation, which we're going to call the Haar wavelet. Any questions before we get started? Okay, well, let's go. And so the first thing we're going to do today is we're going to talk about this particular general form. So, oh, where am I? There am I. So if a dilation equation is of the previous form, is of the form sum over k equals 0 to d minus 1, ck f of 2x minus k, then we say that all dilations in it, dilations in the equation, are factor 2 reductions. Okay, so everything is shrunk by a factor of 2 each time. You can have more complicated dilation equations, but of course, this is the simplest non-trivial one. And let's go ahead and prove something about the coefficients. So I think this is lemma 11.1 in your textbook. So we're back to the Bloom, Hopcroft, and Cannon textbook for most of the wavelet lectures, though I might supplement with some other sources as well. So if we consider a dilation equation, f of x is equal to this particular form. So it's a dilation equation where all dilations are a factor of 2 reductions. Then, Euler, we have that the sum of all these coefficients, k equals 0 to d minus 1, ck, is equal to 2. Or we have that the integral from minus infinity to infinity of f of x dx is equal to 0. Okay, and if you look at the two examples we had earlier, well, both of them happen to satisfy this condition, where the coefficients, in this case, 1/2, 1, and 1/2 add up to 2. Or in this case, where just 1 plus 1 is equal to 2. But you do have non-trivial solutions that match either of these. So you can have both of these generate non-trivial dilation equations that are of interest. So let's go ahead and prove this. And the proof is fairly straightforward. It's just a matter of taking integrals. So the integral from minus infinity to infinity of f of x dx, well, that's just equal to the integral from, we can substitute that our summation in, ck f of 2x minus k dx. And it turns out that if the one norm of the function is finite, then we can swap the integral and the summation. So the summation integral, k0 to d minus 1 minus infinity to infinity ck f of 2x minus k dx. So you can't, of course, like you've taken analysis, you can't always swap these things, but in this particular case, you can because we're looking at functions whose one norm is finite.
Is the fact that it's a finite sum?
Does that always fix it? Oh yeah, that also always works for this particular case, where we're only going up to d minus 1. Yeah. So regardless, we're allowed to swap these the summation and integral, and we can pull things out. Let's just ck integral minus infinity to infinity of f of 2x minus k dx. But of course, since we're integrating from minus infinity to infinity, translations don't matter. So we can get rid of that part of it. So ck integral minus infinity to infinity of just f of 2x dx, which is equal to 1/2 times the sum from k equals 0 to d minus 1 of ck integral from minus infinity to infinity of f of x dx, which basically proves the theorem because then that's equal to the integral from minus infinity to infinity of f of x dx. And so therefore, either this part has to be equal to 0 or the sum of the ck's has to be equal to 2. So then either the integral is equal to 0 or the summation k 0 to d minus 1 of r of our ck's is equal to 2. And both are allowed and give non-trivial solutions. Non-zero solutions. Okay, so let's just one fact about the general form of these coefficients. We're going to talk about some more of those next time. So on Wednesday, when we talk about dilation equations and wavelets in general. But for today, we're going to focus on this easy example, this one here, and actually spend some time to construct a basis out of it. So all we have right now is a dilation equation. We don't actually have an orthogonal basis. And so we'll see how we can actually construct an orthogonal basis out of this thing. And this will be called the Haar wavelet. Okay, so we're going to let, first we're going to let a scale function. Scale function, let's call it phi of x, be a solution to f of x is equal to f of 2x plus f of 2x minus 1. So for example, this could be phi of x is equal to 1, 0 for 0 less than or equal to x less than or equal to 1 otherwise. So we have some scale function, but we're not going to specify the exact nature of it yet. Let's just one example. And we're going to define shifted and scaled versions of this. Phi sub jk of x is going to be equal to phi of 2 to the j x minus k. And note that we'll throw in a factor of 2 to the j over 2. So this is going to be needed later for the orthonormal basis, but it's just easier if we don't worry about that scale factor. So obviously, if you have an orthonormal basis, its inner product has to be with itself has to be equal to 1. And so that's why we need to do this rescaling. But for the purposes of just figuring out orthogonality, that obviously doesn't matter. They needed later for the orthonormal part of this basis, but ignore for now. Because we're just going to try to show orthogonality, because we're not even at the point of orthogonality yet. Okay, so what have we just defined? We've defined a bunch of shifted and scaled copies of this function. That's just one. If we're actually using this function, that's one on the range from 0 to 1 and 0 elsewhere. And now we might ask, what are the spans of this family of functions? So we're going to let Vj be equal to the span of all the phi jk's for over k in the natural numbers. So something like v naught is equal to the span of phi 0, 0, phi 0, 1, phi 0, 2, and so on. And when you draw this out, if we're going to use our basic function again, this is going to look something like, let's do. And so on. So this one here is phi 0, 0. This is phi 0, 1. This is phi 0, 2. Because you're just translating them over. Let's see. And phi1 would then be the span of things at half of this. Phi 1, 0, phi 1, 1, phi 1, 2, etc. And so that's going to look something like this. Okay, and of course this here is phi 1, 0, phi 1, 1, and so on. And now there are a couple of nice properties that are pretty obvious, but let's go ahead and state them because they'll something like this will be true for more complicated examples as well. So obviously the span of the phi 0 i's is going to be contained in the span of so it's going to be contained in B1, which is going to be contained in B2, and so on. And this is a fact that's guaranteed by the dilation equation, right? So basically, if a function can be constructed out of these things, then you can certainly construct that function out of these things. Is everyone happy with that?
Why aren't the spans like equal?
Oh, because when you're taking a span, you're taking a linear combination of them, right? So a function that looks like, let's see.
This is kind of like the when we talk about Riemann integrals taking partitions.
Yeah, exactly. So it's sort of like if you can sort of think of it as like Riemann integrals, because right now these are fixed with rectangles, right? And so this thing here is clearly in the span of lat, right? But it's not in the span of lat. But anything you can construct out of the top one, you can definitely construct out of the bottom one because you just take each pair and plop them together, and then you have the basis for your other other set. And this turns out to be, in general, like this type of thing is guaranteed by the fact that it's a dilation equation. Because the original function can be written in terms of scaled and shifted copies of itself, for any dilation equation, you get this property that as you go down the levels of the dilation equation, as you scale down, well, clearly the higher levels can be constructed out of the finer grained levels.
Well, you just take the two out of the coefficients.
Oh, yes. So for this really easy example, you just take the two neighboring coefficients, you add them together, and then you get the coefficient in the new basis. Yeah. But this fact turns out to be in general true for dilation equations. And obviously in those cases, you might have to do some more complicated operation on the coefficients. What we've done is we've basically constructed a series of spans. And let's talk now about orthogonality, since we want to construct a basis and not just a set of vectors that spans something. So, well, what is orthogonality? Hopefully you guys all remember this, but let's go ahead and define it for functions. So we can define orthogonality with respect to any inner product. Inner product. And so we're just going to use a super standard one. So the inner product of f and g is just going to be integral from -∞ to infinity of f of x times g of x dx.
This is the standard one on function space.
It's one of the standard ones on the function spaces. So yeah. I mean, you can just sort of think of it as like a dot product. I mean, it basically is a dot product. So then f and g are orthonormal, are orthogonal, if the inner product, if the inner product f and g is equal to 0, and they're orthonormal. Orthonormal. I feel like I've been bad at spelling lately. I'm not entirely sure why. If they're orthogonal, and well, the inner products of both f with itself is equal to 1, and the inner product of g with itself is equal to 1. Okay, and so for orthonormality is the reason why, like, we do want this rescaling parameter later, but we don't need it now yet. And so we're going to mostly talk about orthogonality because once you have an orthogonal basis set, it's easy to construct an orthonormal and just start rescaling everything. Okay, and well, let's figure out, are these things orthogonal? Well, some of them are. So phi jk and phi jl, lat is equal to 0 for all j not equal to l, because they aren't overlapping, because non-overlapping supports. So clearly when you take the product of the two functions together, and it's just going to be identically 0, and so the integral is also going to be equal to 0. So that's easy. So we know that this set, phi j0, phi j1, etc., is actually a basis of Vj. And appropriately scaled, it's an orthonormal basis. And so the other thing that you'll notice is that the span of phi jk over all j and k is equal to the space of functions up to some approximation error. Space of functions, but is not a basis because of linear independence. And here we mean a Schauder basis, which means that it's countable. So we're not going to go into too much functional analysis here, but basically, like, you have to be careful about defining infinite bases in function spaces, and we're just going to sweep all of that under the rug. But so the idea here is that we do have a basis for the space of functions. We do have something that spans the space of functions up to approximation error that you can get down to 0 by just taking finer and finer grained resolutions. But now we want to construct a basis out of these functions, right? And the big problem we have here is that phi jk is equal to phi j plus 1, 2k, plus phi j plus 1, 2k plus 1, right? And this is by definition, because that's how we constructed each of these things. Or not quite by definition, but this is because of the scaling factor. And so because of our dilation equation, you know that your higher level can be constructed by your lower levels. That's all we were saying here, that, well, clearly if this span is contained in that span, well, then everything in this span has to be linearly dependent on the things in V1. And so we don't have linear independence. So well, what can we delete? Well, there are some suggestions. So could we delete phi jk for all of these triples? Right, because like we have a bunch of these relations that show that these three
like the process doesn't terminate.
Yeah, so the problem is exactly this process doesn't terminate. Doesn't work, since we are left with only something that looks like phi infinity k. And well, that's not very fun to work with, because we're basically saying, oh, well, if you delete down to just infinitely wide, infinitely fat rectangles, well, clearly you can construct any function you want out of that. That's not super interesting. So instead, what we're going to do is we're going to delete one of the other ones. So we're going to delete phi j plus 1, 2k plus 1. So we're going to delete this one here for all of these triples in a systematic way from our set of functions for all k, basically. So for each of these triples, we're going to delete that. And so basically we're removing all of the phi jk where j is greater than 0 and k is odd. So we're deleting all the odd ones. And it turns out that that will actually give us a basis that is a bit nicer to work with. So then we get the set phi 0, 0, phi 0, 1, phi 0, 2. So it doesn't change anything about the first level. But in the second level, you have phi 1, 0, phi 1, 2, phi 1, 4, and so on. And so in all the lower levels, you've deleted all of the odd ones. And it goes on forever, obviously. And so what does that look like? Well, what that looks like is, let's see if I can draw this on my grid. There's a reason I have grid paper on here. So you might start with these, right? Oh, wait, 1, 2, 3, 4. Let's actually make these square. 2, 3, 4. So you still have those functions. And then you also have these functions. And then you also have these functions, and so on. And so clearly you still can construct anything that you would have constructed out of the previous set, except now you have like now you have a basis that you actually can work with, because you can order it, you can count on it, and so on. But this still doesn't get us an orthogonal set, right? So the problem now is phi jk phi j plus 1, 2k is not equal to 0. So not an orthogonal basis. Right? Because if you take the integral of lis times lat, that's not going, well, the product of those two things is just going to be lis, and the integral of lat over from minus infinity to infinity is not going to be equal to 0. But we know how to, we've all taken linear algebra, we know how to construct orthogonality out of this sort of set. Yeah, so something like Gram-Schmidt, and it turns out that it's actually even easier than that because of the smaller set of relations that we have to worry about. So instead, note that the span of, and I'm just going to draw this pictorially. So the span of this thing and this thing, which are not orthogonal, is equal to the span of the first one is left unchanged, and the second one is that thing. And this is basically where we get wavelets from. So what we're doing is we're just subtracting out a, basically we're taking things and subtracting them out with each other. And the nice thing about this is you'll note that this set is actually orthogonal, right? Because when you multiply these together, half of it's positive and half of it's negative. You take the integral, you get 0. And so then you're happy. So that gives us basically the full set of things that we're going to be building in order to get a orthogonal or orthogonal basis. So now what we're going to do is we're going to let y sub jk of x be equal to, and this is going to be a little bit more complicated. It's going to be 1 between 2k over 2 to the j. It's less than or equal to x. It's less than 2k plus 1 over 2 to the j. It's going to be minus 1 for 2k plus, between 2k plus 1 over 2 to the j and 2k plus 2 over 2 to the j. And it's going to be 0 elsewhere. Elsewhere. Okay, and we're going to replace phi sub j plus 1, 2k with phi sub j plus 1. Oh, sorry, yeah. Have I been saying phi? I mean psi. So this psi. Okay, not a y, that's a psi. So standard notation, we're using phi and psi for these basis functions. So replacing all the phi's with our psi's. So we get an orthonormal basis. Come on. An orthonormal basis. That is, we still have the phi's on the first level because we don't need to worry about those. Phi 0, 2, and so on. But then in the lower levels, we have these psi's instead. Psi 1, 0, psi 1, 2, psi 1, 4, psi 2, 2, 0, psi 2, 2, psi 2, 4, and so on. And this actually does turn out to be an orthonormal basis. Furthermore, we know that for any finite support function, we can approximate it by choosing a scale vector or phi whose scale is that of the support of the function. Right, so what do I mean by that statement? What I mean by that is if I have some function that looks like something crazy, oh, I need to actually draw a function. If I have some function that looks like something crazy, but it has finite support, then all we have to, then instead of choosing our normal blocks, which look like that, well, all we have to do is we just need to choose a scale function that has support like that. And then we can use that and scale it down and create and approximate this red function by just taking by using this basis generated off of a phi of x that starts out as this thing. I guess I'll leave that here. That doesn't need to be that tall. That doesn't really matter how tall things are, obviously. I guess you'd want it to be however tall it needs to be orthonormal, but we're not worrying so much about that right now. So let's see, so it's straightforward to approximate with the phi sub jk of x for fixed j, right? So just think of it like Riemann sum. So of course you can approximate this thing by saying, well, let's see, what's its height here? Its height here is there, and then maybe the average height here is there, and so on, or whatever. So clearly you have some approximation, and how exactly you choose the size of the rectangles, it does make a difference, but it doesn't make so much of a difference as you choose smaller and smaller rectangles. Depends on exactly what you're going to do, but basically think of it like Riemann rectangles. So you can approximate your function using finitely many rectangles, depending on what you want to do. And this is equivalent to a 2 to the j point sample, evenly spaced. So now if we were thinking about this in sort of a more applied setting, oftentimes you don't actually have the entire function. What you have is some sensor that is taking snapshots every like 10 milliseconds or something. And so then what you're basically doing is you're approximating some function over time by taking each of these snapshots. And it turns out this is quite nice for something like a wavelet basis, or something like the Haar wavelet basis at least, because, well, that is precisely the set of snapshot. The set of snapshots precisely gets you the coefficients in front of the everything at that particular scale level. When you're taking the linear combination of those particular basis functions. So what do we know? We know that f of x, and now the f of x here is not our scale function. F of x is the function we're trying to approximate. So f of x is equal, not equal, it's similar to, it's approximately the sum over k equals 0 to 2 to the j minus 1 of sk times phi of 2 to the j x minus k, which we can write as a vector s naught, s1 through to s to the 2 to the j minus 1. So, and this thing here is directly measurable, right? So what we're doing is we're only looking at the phi sub jk scale functions at the scale level j. And we're just measuring a bunch of times, and that gives us some approximation for the function. Of course, this approximation isn't in our wavelet basis. This approximation is in, well, this basis, right? Or it's not even actually in this basis yet, because you might even have the ones where you have an odd second index. But it's so what we're actually doing is we're approximating it in Vj. So we're approximating it in this Vj span. Sorry, I have so many notifications today. We're approximating it in this Vj span. But of course, that isn't the basis that we want, because and so what we want to do is we want to convert all this over into the original into our wavelet basis. And so to rewrite this, we rewrite in the Haar basis, let's say over the unit interval, just because we're rescaling everything anyway. Unit interval, we need to find CIs. So this is just a change of basis. That's all this is. So we're just going to do change of basis. And of course, one of the other things you have to be a little bit careful of is for an orthonormal basis, for functions supported on 0, 1. Well, we're going to have phi of x is going to be the standard thing 1 from x greater than or equal to 0 less than 1, 0 otherwise that's normally a less than, not a less than or equal to. And we're no longer going to need all of these things, right? We're only going to need the ones that have support on the interval 0, 1. And so that means that we have a much smaller list of basis. We just end up with a much smaller list of basis vectors that we need to worry about. And so we get the thing. Oh. So we get phi 0, 0, and we need psi 1, 0. And note that these things both have support length 1, right? So this is because one of these is that, and the other one is this. So they both have support 1. And then you look at the ones with support 2, which is going to be psi 2, 0, psi 2, 2. Yeah. And these have support length 1/2 for each of them. And those look, well, like that, just thinner versions. And so on. And you can keep on going. And so like psi 3, 0, 3, 0, 3, 2, psi 3, 4, and psi 3, 6 is going to have support length 1/4, and so on. Oh, and each time at each level, you're going to be doubling the number of basis vectors that you need, right? So if you were to keep on going psi 4, 0, you'd have to go all the way through by 2s. So psi 4, 2. Psi 4, 14. Yeah, so you're going to have 8 of them, but the indices are going to go up through 16 because we're going by 2s. And this is going to have support length 1/8, and so on. But this does tell us what exactly, so if we're going to rewrite it in the basis for the function supported on 0, 1, you just stop at whatever level here that you care about. So maybe you stop there. Actually, where do we stop here? Yes, that is where we stop. So we can stop there. And that gets us the approximation where we were at the scale level where each of the supports of our phi sub jk's was 1/4. Okay, so now we need to rewrite in the Haar basis. And so, well, this is just a big linear algebra problem now. So because we now have a finite number of vectors, right? And we know how these vectors are all composed, all these basis functions are composed from the other basis functions. And so this is just going to be an exercise in linear algebra. Though there are some tricks that actually make things a little bit nicer because of the self-similarity of the Haar basis, as well as the self-similarity of any wavelet basis. So you could rewrite this as a giant linear algebra problem, S0, S1, S2, S3, S4, S5, S6, S7. This is going to be equal to some transformation matrix and times, actually I might need more space than that, but it's going to, over here, we're going to have C0, C1, C2, C3, C4, C5, C6, C7, right? And what we want to do is, well, what is phi of 0, 0 in terms of the, what is that equal to as linear combination of all the phi sub j, phi sub 3 k's? So notice that phi sub 0, 0 is equal to phi sub 3, 0 plus phi sub 3, 1 plus phi sub 3, 2 plus phi sub 3, 7, right? Because what you're doing is you start off with, let me make this bigger. You start off with listing, and you're basically asking, well, how many of these do I need? Well, you need exactly 8 of them to add up. And I didn't draw this well, but that's the basic idea there. And so that means that, of course, with this change of basis, we're doing the change of basis in the wrong way right now, but that's the easy way of like constructing these things. And so we have coefficients 1, 1, 1, 1, 1, 1, 1, 1 as part of our change of basis matrix. What about, so that was phi sub 0, 0. What about psi sub 1, 0? What are the coefficients for that going to be when you're constructing that thing? So remember, that thing looked like this.
1/2 on each side.
1/2 of what?
I just meant, is it 1/2 on each side? Like,
Yeah, so it's 1/2 on each side.
1, 1, 1, minus 1, minus 1.
Yep. So it's going to be 1, 1, 1, 1, minus 1, minus 1, minus 1, minus 1. And of course, we have to keep on going. So there's phi of 2, 0, and psi of 2, 2. And each of these are going to look the same as our psi of 1, 0, except they're going to be 1/2 and possibly scaled, right? And so you're going to get one that's 1, 1, minus 1, minus 1, 0, 0, 0, 0. And the other one's going to be 0, 0, 0, 0, 1, 1, minus 1, minus 1. And so on. So we also had psi 3, 0, psi 3, 2, psi 3, 4, and psi 3, 6. And each of these is the first one is going to be 1, minus 1, 0, 0, 0, 0, 0, 0, 0, 0, 1, minus 1, 0, 0, 0, 0, 0, 0, 0, 0, 1, minus 1, 0, 0, 0, 0, 0, 0, 0, 0, 1, minus 1. Okay, so list allows you to transform from the, list directly allows you to transform from the Haar basis into the evenly spaced basis. And you notice, of course, that we can't, you end up with a single pair of 1 minus 1s. Like if you needed to go down even further in resolution, you'd have to have, well, twice as many of the basis vectors, of course. But so now, this unfortunately is the wrong direction because we don't want to transform from the Haar basis over into our evenly spaced basis. We want to do the other way. And you can take a matrix inverse. So this is an invertible matrix, but that's really rather slow. And there are more clever ways of doing this transformation than actually taking a matrix inverse. And that's basically due to the fact that we have this pairwise relationship between all of these sets of basis vectors. And so there's actually a really fast algorithm for doing this that basically involves first drawing out a binary tree. S0, S1, S2, S3, S4, S5, S6, S7, because these are the original samples we have, right? And what we're going to do is we're going to construct a tree by taking the average of every pair of elements. So this is going to be S0 plus S1 over 2, S2 plus S3 over 2, S4 plus S5 over 2, and S6 plus S7 over 2. And we're going to repeat until we get down to just a single term. This is going to be S0 plus S1 plus S2 plus S3 over 4. This one's going to be S4 plus S5 plus S6 plus S7 over 4. And lastly, you're going to get S0 all the way through S7 over 8. And it turns out, and this takes a little bit of thinking, but this thing here is actually equal to your coefficient C0. This one's perhaps a little, basically because if you go back and look at how these things all work out, when you take the matrix inverse, this thing is going to be your coefficient C0. And if you take list subtraction here and divide it by 2, then this thing is going to be equal to C1. If you take list subtraction and divide that by 2, that's going to be equal to C2. If you take list subtraction divided by 2, this is going to be equal to C3, and so on. So this is going to be divided by 2, it's going to be equal to C4. List subtraction divided by 2, that's going to be equal to C5. The subtraction divided by 2 is going to be equal to C6. And the subtraction divided by 2 is equal to C7. Okay, and like it does take a little bit of staring at this to really be convinced that this is actually giving you the inverse of this matrix. But it's basically taking advantage of the fact that each of our basis vectors is constructed in this very nice way from this evenly spaced basis. And let's see, that is actually all I had prepared for today. So are there any questions about this? So next time, this is actually a fairly natural point to stop because next time we'll be talking more generally about wavelets. So not just focusing on the Haar wavelet, but proving facts about the coefficients of like general dilation equations and the wavelets they generate. But I think I will actually end class early today.
So in practice, we never actually write the matrix, we just do the binary.
Yes, so in practice, you never actually write the matrix because you don't need to. And the same would be true. So like, we've obviously done this in the easiest possible case, which is the case of the Haar wavelet. But even for other more complicated wavelets, because of the dilation equation, because that's how we've defined them, because of that, there is generally a faster way of computing doing this matrix inverse than actually writing everything down. So it's basically due to the fact that when you have this kind of self-similarity, of the dilation equation, wherever I put that. Whenever you have this kind of self-similarity, that actually makes a lot of computations a lot nicer. Okay, so I will go ahead and end today because that is all I had prepared. So class is ending early today. It's a Friday. Hope you enjoy your weekend. And next Wednesday, we'll go back to talking about wavelets more generally.